Hey, today we're going to talk more about two quantitative variables and scatter plots, and specifically linear regression. So I've taken a problem from the book here, from page 199, number 17, and I've just taken the two quantitative variables, the number of salespeople working at a store, and then the amount of sales they make in a day in thousands. So two people working at the store brings in $10,000. So on and so forth. So we have so far been able to put those into lists in the calculator and create a scatter plot. And our scatter plot looks like it's positive, looks like it's linear, looks like there's a pretty strong correlation, association, between the two, number of salespeople working and sales. It's important to note that my x, or my explanatory variable, the x-axis, this horizontal axis, is the number of salespeople, and the dependent response variable is our sales. And so we've met all of our conditions. These are quantitative data. The scatter plot's straight enough. There are no outliers. And so we could calculate an R value, which we did in the last lesson. And it's positive. It's very strong, very close to 1, 0.9653, so on and so forth. So the next step is we would want to find a linear model, the equation of a line that best represents our data. So we want to find the equation of a line that best represents the relationship between the number of salespeople working and the amount of sales that they had at the store. And when we calculate the R value, we also get an A and a B. And you can see up here, they write this equation where A and B is in there, and that is actually our linear model, and we can plug in the values that we get. So 8.1 is an intercept, as you'll know from algebra, and the 0.9134 is a slope. X represents the explanatory variable, which in this case is the number of people working, and Y is the dependent response variable, the number of sales. If we put a hat on here, because any value we get for Y is going to be considered a predicted value. We can plug X values in here for potential number of workers, and it could give us a predicted value of how much the company would stand to make that day with those number of workers. It's not always correct, because as you saw in the scatter plot, the line isn't perfectly straight. And so that line, if we graph it along with our scatter plot, you can see it's not going through all the points. Some are above and some are below. And so if we wanted to predict how much money this company would make, we could plug in the number of workers for X and get a predicted Y hat for sales. Just want to give you some names we might use to talk about this line. It's a linear model, sometimes referred to as prediction equation, because we can make a prediction based off of it. The line of best fit, the least squares line, or a regression line. And the one thing I wanted to point out about this line of best fit or regression line and its relationship with the data points is some are above and some are below. There are a couple who are right on the line. And so if I look at the distance, if you can see that blue line, the distance between any data point and the prediction line or the regression line is called a residual. So we have some above and some below, and so the points below will have a negative residual, the points above will have a positive residual, and the points that are right on the line will have a residual value of 0. And it just sort of speaks to the distance that that data point is away from our predicted line. We'll talk more about residuals here in a minute or so. So we are always talking about things in context in statistics, and so X and Y hat don't really give us a lot of context. And since we are talking about the number of people working and the number of sales, we can rewrite this in context. Workers was our explanatory variable X, and sales is our response variable Y. Again, it's sales with the hat on it, because it's just going to be a predicted value. Anything that we get from this equation is going to be a prediction for sales. It's not going to be exactly how much they make. And so a couple things we want to analyze about this regression line is, what does the slope mean? And so if we want to interpret this slope in context, for every worker, every extra worker we plug in here, where it says workers, we're going to multiply that by 0.9134. And that's going to increase our sales by that value of 0.9134. And if you remember on the first page, the sales were in thousands of dollars. So if I multiply this by 1,000, it's $913.40. So what this slope means is that for every additional worker I add working that day, we could expect to make $913.40 more sales that day. It doesn't mean it's definitely going to happen, but that is what we could predict. And then we want to talk about the intercept, 8.1. Again, we're in thousands of dollars here, so this means $8,100. And if you remember back to algebra, intercept is where the line crosses the y-axis. So let's actually go back. You can see right here where the line crosses the y-axis. That is our intercept. And so to interpret that, we would say that if nobody showed up to work, the company would make $8,100. And so that actually doesn't really make sense. And that's okay. As long as we understand that this is not making sense if we have 0 workers, that's okay. These predictions equations sort of need to be taken with a grain of salt. So you wouldn't want to plug 0 here and say, hey, if nobody shows up to work, we're going to make $8 grand. That wouldn't make any sense. So I said we talk about the residuals a little bit more. And so here's a way we could calculate. E stands for error. Y is the actual data point, the actual Y value, and Y hat is a predicted value. So if we plugged in, let's say, 3 workers to our sales equation, if we plugged in 3 workers, we would get a total number of predicted sales. And then we could go look, and I'm going to go back. We can go look at the amount of sales we actually had for 3 workers, so 11,000. We could subtract the 11,000 minus the predicted value, and we would get a residual. If the residual was positive, that means that our data point was above the line. If the residual is negative, that means our data point is below the line. And so there's a way to actually calculate all the residuals in the calculator, and I will show you that in class. So here in my list 3, I wrote an equation that took all my values from list 1, all of my X values, all of my number of workers, and it was plugged into the prediction equation. So you can see here for my first, I believe it was 2 workers, they made $10,000. This equation predicts that they make $992. I'm sorry, they made $10,000. And this would predict they made $9,926.80, giving us a positive residual. The actual score, or the actual number of sales, 10, was above the predicted value of 9.9268. This L4 was created by simply subtracting L2 minus L3, and these decimals, some positive, some negative, are all the residuals. And so sometimes we want to know, hey, is our line good enough? How well is it fitting the data? You know, how much should I believe in this prediction line, this regression line? And so one thing we could do is we could take this list of residuals and create a scatter plot using the original explanatory variable measures, so L1 that you can't see over here, the number of workers, against the residuals. And so we get what we call a residuals plot. It should look like a scatter plot. And the better our equation, the better our line fits our data, the less this is going to look like it has any sort of pattern. So we don't have a ton of data points in this data set for simplicity's sake. So there's not as many points on here, but there's not really a pattern to this plot of number of workers and then the residual sales. So our equation looks like, and we can feel pretty comfortable about it fitting our data pretty well. That's it for today. We're going to do some examples in class, create some more scatter plots together, calculate some correlations, and come up with some regression lines.